Hi everyone, I am Saina VK, first MCA student at Kannur University campus Mangaturumba. Here I am describing about linear transformation, related metrics and eigenvalues or eigenvectors. Linear transformation is a special kind of function P that maps vector from one vector space to another while preserving two main operations. The operations are one is vector addition and another one is scalar multiplication. In vector addition, P is a special kind of function. U and V are the two vector spaces. For vector addition, T of U plus V equal to T of U plus T of V. In scalar multiplication, C is the scalar. T of Cu equal to C into T of U. Matrix representation of the linear transformation. Matrix representation is a way of writing a linear transformation as a matrix so that we can use metric multiplication instead of applying the transformation manually. P is a special kind of function. Here r raised to m and r raised to n are the codomain and domain. M and n are the rows and columns of the matrix. Here it is. Here the matrix A, matrix representation. Then for any vector u, P of u equal to A of A into u, vector u. Here A is the matrix given and U is the vector. For example, let T is a special function. It maps from R3 to R2 by be defined by P of A1, A2, A3 equal to 2A1 plus 3, A2 minus A3 and A1 plus A3. Here we want to find the matrix which represents T, where r raised to 3 and r raised to 2 are assigned with the standard ordered basics. Here this is in the standard ordered basics. So r3 and r2 are the codomain and domain. Here it will be a 2 by 3 matrix. It has 2 rows and 3 columns. These are the options. We want to calculate this and find which is a suitable matrix from the options. For calculating, here I already told that here it is assigned as standard order basics. The standard order is like this: 1 0 0 0 1 0 0 0 0. So first we want to substitute that E of E1 equal to 1 0 0. Step 2 is we want to plug into T of A1, A2, A3. Then replace it with 1 0 0. We can compute the value and we get 2 1. By calculating each of this, first one, T1 0 0, we get 2 1. T0 1 0, we get 3 0. T0 0 1, we get minus 1 and 1. Then the matrix will be a 2 by 3 matrix. It will be 2, 3, minus 1, 1, 0 and 1. The option A is the correct one. Option A is the correct one. By calculating like this, we get this matrix, last matrix as 2, 3, minus 1 and 1, 0, 1. Here, option A is the correct answer. I hope you understand about linear transformation and the matrix representation of linear transformation. Then we are moving to the next portion, eigenvalues and eigenvectors. Sometimes when we apply a linear transformation, the vector does not change its direction, only its length changes. Such vectors are called eigenvectors. Sometimes a linear transformation is applied, the vector does not change its direction, only its length changes. Such vectors are called eigenvectors. Here is the representation. A of vector u equal to lambda of u. Here A is the matrix and u is the eigenvector, lambda is the scalar and it is the eigenvalue here. How to find eigenvalues? To find eigenvalues, we want to solve the characteristic equation, determinant of A minus lambda I. Here A is the matrix given, lambda is the scalar, and I is the identity matrix, which is equal to 0. If it is equal to 0, then we find the eigenvalues. To find eigenvectors, after finding eigenvalues, substitute each lambda into A minus lambda I of vector u equal to 0. Solve for eigenvector u. After finding or calculating the eigenvalues, by using these values, we get two eigenvalues. By using these eigenvalues, we can find the eigenvector by substituting the values into the lambda. Here is a simple example. Here the given matrix is 5, 4, 1, 2. To find eigenvalues, we want to transform it in the form of A minus lambda I. Here A is the given matrix, which is the above matrix. Lambda is a scalar and I is the identity matrix. By multiplying the lambda by identity matrix, we get lambda 0, 0 and lambda. By minusing the given matrix and the identity matrix, which is calculated by lambda into I, we get 5 minus lambda, 4, 1, 2 minus lambda as a new matrix. For this new matrix, we want to determine the determinant. It is the basic formula that we multiply diagonally and minus with the other diagonal multiplication. Then we get 5 minus lambda into 2 minus lambda minus 4 into 1 equal to 0. Here the lambda's value we didn't know, so we want to expand it as by multiplying this. Then we get 10 minus 5 lambda minus 2 lambda plus lambda square minus 4 equal to 0. By calculating this, we get lambda square minus 7 lambda plus 6. Here, the final equation we get is a quadratic equation. We already know how to solve a quadratic equation with the formula minus b plus or minus root b square minus 4ac by 2a. Here we are using this formula. I have already told, here we get a quadratic equation and we are solving the equation by the well-known formula minus b plus or minus root b square minus 4ac by 2a. Here we get the values of a, b and c. By substituting these values in the equation, we get the lambda value. We get two values for lambda. One is by adding and one is by subtracting. The two values the first value is 6 and the second value is 1. By solving using the quadratic equation, we get two values for lambda. One is 6 and one is 1. Here we get the eigenvalues. I have already told that by using the eigenvalues, we can determine the eigenvectors. We want to calculate the eigenvectors too. So, by using these values, we are calculating the eigenvectors. Here, the given matrix is already given matrix 5, 4, 1, 2. Eigenvector equation is A is the matrix given, lambda I is the scalar into identity matrix, and xy is the vector we use. Here is the formula A minus lambda I into xy, the vectors equal to 0. We want to calculate this equation to get the eigenvector. I have already told that we want to substitute the eigenvalues to the lambda. Then we can calculate the eigenvectors. The first value we get for lambda is 6. By substituting 6 into the space of lambda, we get a minus 6i. Then we get minus 1, 4, 1, minus 4 is the matrix. We want to multiply it with the vector x and y. By multiplying, we get minus x plus 4y equal to 0. Here x equal to 4y, let y equal to 1, then x equal to 4. Eigenvector for lambda 6 equal to, we get v1. By substituting the first value, we get v1, the vector 1 as 4 and 1. Again, we want to substitute the lambda with the second value we get, that is 1. By substituting 1 in it, we get 4, 1 and 4, 1. Then again we want to multiply it with the vector. We get by 4x plus 4y equal to 0. X equal to minus y. Let y equal to minus 1. Then x equal to 1. Eigenvector for lambda equal to 1. Here we get v2 by substituting the second value for lambda 1 and minus 1. The final answer is eigenvalue is 6 and 1. By calculating eigenvector by using the eigenvalues is 4, 1. The first one, v1 is 4, 1 and v2 is 1 minus 1. I hope you understand. Let's once again revise it. If we get a matrix, first transform it into form A minus lambda I. A is the given matrix, lambda is the scalar and I is the identity matrix. Then determine its determinant. By calculating or expanding, we get a quadratic equation. By the well-known formula to solve the quadratic equation, minus b plus or minus root b square minus 4ac by 2a, we are calculating the values of lambda. By calculating or substituting the values into this equation, we get two values for lambda. These values are the eigenvalues. By using these eigenvalues, we are calculating the eigenvectors. For this, we want to transform it in the form of A minus lambda I and also adding the vector x and y. By substituting the eigenvalues into the position of lambda, we get v1 and v2. By substituting first value, we get v1. By adding or substituting the second value, we get v2. Then this is the final thing. By solving the quadratic equation, we get the eigenvalues, and by using the eigenvalues, we get the eigenvector. In short, linear transformation maps vector while preserving line properties. Matrix of T represents transformation in matrix form. Eigenvalue, stretching factor for a vector under transformation. Eigenvector is a direction vector that doesn't rotate during transformation. I hope you have understood what is a linear transformation, matrix representation of a linear transformation, eigenvector and eigenvalues. Thank you for watching.